This is our chapter 1 review, and we are going to start with notation. So we have -5 is less than x, less than or equal to -1, or x is greater than or equal to 7. So if we make a quick chart, 2, 3, 4, 5, 6, 7, to show what this looks like, we would have an open circle at -5, a closed circle at -1, and x is anything between there. So we would shade that, and then it jumps, and x is greater than or equal to 7. So we'll go ahead and just extend that a little bit, and that's what our graph would look like. So anything in this interval up to and including -1, and then it jumps and it's 7 or anything greater than 7. So that's what it looks like. So in interval notation, we get rid of all of the inequality symbols. We don't use the idea of opener circles. We jump into parentheses and brackets. And interval notation always goes from low to high. All right, always low to high. So the lowest of the interval is at -5. And because it's not included, we use a parenthesis, almost like an open circle. And the highest in this interval is -1. It's included, so we use a bracket. Remember, the bracket almost looks like an equal sign, and there's your line there. Then we use the union symbol, okay, U standing for union, which is in place of the word or. And then the second interval starts at a low of 7, and it goes up to infinity. The 7 is included, and it goes to infinity, and since we can never reach infinity, it is a parenthesis. We cannot equal that. I cannot do this in roster notation, non-applicable. The reason it doesn't work in roster notation is because this is continuous. Okay, it's not discrete, and there are infinite points between -5 and -1. There are infinite points between -2 and -1, -0.9999, and we could be here all day naming those. So interval notation, listing them will not work. Typical roster notation will not work. Typical roster notation is when you have your brace and you list the numbers that it can be and then close it. All right, in set builder notation, you use your brace and you would state x such that, and you really could just put this right in there. -5 is less than x, which is less than or equal to -1, or x is greater than or equal to 7. And we could put it in words. In set builder notation, there's lots of things we can do. How do I write in words? Exactly as I said it. -5 is less than x, and x is less than or equal to -1. Guess I could write that out. So we'll just write out -1, or x is greater than or equal to -7. It's a lot to write out. Or equal to, sorry, just 7. Okay, so that's how I can write out in words. So roster notation can only be something that you can list, something that is discrete. And the minute that you have something that's continuous, even though it starts and stops, it is continuous, so it cannot be done in roster notation. All right, identify the sets that these numbers belong to. So we know that they're all real, but I'm going to list that anyway. Real is a symbol that's a double-lined R, so all of these are real numbers. My next decision is, are they rational or irrational? Rational numbers can be written as a fraction. It can be a terminating or repeating decimal. So here I have a terminating decimal. It ends at 0.5. So this would be real, and it would be rational. The symbol for rational is a double-lined Q if you're using that. All right, now if we go to part B here, I know it's real, but I'd like to see what it is. It's really -4/2, which ends up being -2. So it absolutely is rational, but because it is a negative whole number, we would also consider it an integer. And the symbol for integer is a double-lined Z if you're using that. All right, I have pi/3. So if you look at this too quickly, you see a fraction, so you think it's rational. However, pi is irrational. An irrational number is one that never terminates and never repeats. So this is a good example of an irrational number, because anything that I do with pi will continue to be irrational. Then I have this 2.47 repeating. It is rational because it repeats, and that is the end of it. So let's think about this real quick. Integers are positive or negative whole numbers. Whole numbers start with a whole at 0, then go 1, 2, 3, etc. And natural numbers start at 1. So the only difference between a whole number and a natural number is the number 0. And again, integers are positive and negative whole numbers. Okay, we are now jumping into roots. And in order to add or subtract my roots, they have to be the same. So I would need a square root of 2 over here to add. And I don't have that. However, we do need to break this down. So I'm going to bring that 4 square root of 2 down plus something. And I want to figure what that is. It's the square root of 4 times the square root of 2. So we're using our skills to find the biggest perfect square and break it up. Again, we're using our rules. Square root of AB is equal to the square root of A times the square root of B. So I am breaking that up, and that would leave me with 2 square roots of 2. Now I have like terms. I have 4 of these square roots of 2 plus another 2 of them. So I have 6 square roots of 2. And I want to remind you, so we don't get it mixed up, we keep the like terms just like we would if it was a variable there. Okay, the next one is a little different because I have a fraction. So I want to remind you of our other rule that if I have the square root of A over B, that's the square root of A divided by the square root of B. If I have them broken up with division underneath the root sign, I can put them back together. So I don't have to rewrite this, but I'm thinking of it as one big fraction. And before I break up 75 or I rationalize the square root of 3, 3 goes into 3 once and it goes into 75 25 times. So I'm left with the square root of 25 over the square root of 1, which is simply 5. Square root of 25, 5, square root of 1, 1. And that made that problem a lot easier. All right, we're not always going to be able to do that, but the first thing I want to do is try to reduce the fractions. Anything that I have, I always want to reduce those fractions underneath the root sign. And if I couldn't reduce the fraction, then I would try to break up my numbers before I rationalized. Rationalizing is the last thing I want to do. All right, looking at the next one, if we didn't have square root signs here, we could definitely add all these, they're like terms. But because it's a square root of 75x, that is now not a like term with the square root of 27x. So first, the x's are just going to have to stay underneath the root sign. But the thing that I want to do is break down my numbers. So 75 is going to break down to be 25 and 3. And I'm going to leave the square root with the 3x in it there. So that leaves me 5 of these square roots of 3x. And then I'll put up my plus sign here. Next is the square root of 27. So I'm going to go with the square root of 9, square root of 3x. Knowing my perfect squares and knowing my times tables makes a big difference in speed here. So the square root of 9 is 3. Keep that square root of 3x. Minus, we got to break the 24 down. There's several factors of 24, 2 and 12, 3 and 8. The one I care about is the 4. And then I have the extra 6x. Now notice that I always put my perfect square first. It helps keep me straight. And I have minus 2 square root of 6x. So when I go to look for like terms, because I'm adding and subtracting, these two are like terms. So 5 of these and 3 of these is 8 of the square root of 3x. And then I have to leave this minus square root of 6x alone. I know a lot of people want to break down the 6 to be 3 and 2, but I can't take the square root of that, and I would still have those 2 square roots left over. So that is my final answer. We can't always put everything together. Okay, looking at this next one, I have the square root of 2 and the square root of 18. Individually, neither of these are perfect squares, so if I just put them together, I get the square root of 36, and it's much quicker. I just have 6. If I broke the square root of 18 down, that's fine. I would have to put my roots back together and break them down. So those worked out for us pretty quickly. So let me throw an extra one on here. If I had to rationalize the denominator, if I had something like the square root, 2 square roots of 6 all over the square root of 5. If I had this problem, I would need to rationalize the denominator. There's nothing to reduce with the 6 and 5. I can't break these down. So I would come in and I would square it. I would multiply it by itself. So when I go to do that, the top would be 2 square root of 30. We can put these together, and the bottom would simply be 5. This comes together to be the square root of 25. So with that in mind, I now need to double check. Can I reduce my fraction with the 2 and 5? No. And can I break down my root that got put together? This is square root of 30. There are no perfect square factors, so that would be my final answer there. Alright, let's look at an example like this that maybe doesn't come together so easily. So we'll make it a 3 square root of 5 and 15. Okay. So let me box these off. So extra example here, there's nothing I can do with these, but if I put my roots together, 5 times 15 is 75. And so now I can find a perfect square factor to break down. So I keep my 3, I don't want to lose that. Square root of 25 times square root of 3. So I re-broke this down to find factors that work better. This would be 3 times 5 square root of 3, which is 15 square roots of 3. So just wanted to show you something a little harder than these, but sometimes it's that simple. We just have to do a little work ahead of time. All right, we are now talking about the domain and range of the functions. So domain are the x values, so we're going to list it in roster notation. Notice the directions there. And the domain would come from the x's, so -1. We have that -1 twice. I have a -3. Actually, I'd like to put the -3 first. Then -1. And then I have a 3 and I have a 5. So that is roster notation. You only list each number once. The range is the y value, so the lowest y value I have is -1, then 0, 1, 2, and 4. Double check myself. -1, yep, I think I agree. Okay, is this a function? So the question is, does every x have exactly one y? And that is not true. Right here, that is the issue. So why is it not a function? Not every x has exactly one y. When x equals -1, there's more than 1y. That would be why it's not a function. Okay, now we're going to look at this graph here, and we can see that it starts, and that's a closed circle, and then it goes up forever, so it's a ray. So we want to give the domain and range, and notice it asks for an interval notation. So interval notation is always low to high. I cannot do this in I cannot do this in roster notation, because I could not list the infinite points that start here and go in between everything going up this line. So the domain, the lowest value for the x, I always say take your pen or pencil and come across and scan. And the first x value I hit is right here at -3. So the domain low is -3, which is included, and that's why it's in a bracket. And as my graph goes up, it's going to keep pushing out to the right. So it goes to positive infinity, always a parenthesis. The range is your y value, so scan that. We come up, and the first y value I hit is at -2. And again, that is included. And this 2, as it goes this way, it goes up, up, and up, so positive infinity. Is this a function? Absolutely. We could simply say that it passes the vertical line test. We could look and see that every x does have exactly one y. All right, on to the next set. We're in function notation now. So we have two separate problems to do, and we're going to evaluate these problems with each of these x values we're given. So I would like to just write this down. F of -3 equals, and that's going to be a spot for my answer, f of 0, f of 2, and f of 4. So those are going to be spots for my answers that I have all set up there. So when I go to do this, I'm literally taking -3 and I'm plugging in for x. Remember, this is the function of x given 2x minus 4. So if x is -3, I'm going to plug that in. 2 times -3 minus 4, and that'd be -6 minus 4. So I get out negative 10. So you want to show what you've substituted in. Once you throw that in a calculator, you can just get the outcome here, or you could do some work by hand, but watch your order of operations. Do the same thing for 0. Take that 0 and plug it in. 2 times 0 minus 4 gives me a negative 4. And there is my outcome. All right, plugging 2 in. 2 times 2 minus 4. That's 4 minus 4. I get out a 0. And f of 4. So take that and plug it in. 2 times 4. Oh, I did it in the wrong spot. 2 times 4 minus 4. That's 8 minus 4. And that gives me a total of 4. Now I want to remind you, we're done. That's it. Those are my answers. But function notation leads right to an ordered pair. We put an input of negative 3 in, and we got an output of negative 10. Remember, f of x is the same as saying y equals. This is another ordered pair. We put in 0, and we got out negative 4. We put in 2, we got a y value of 0. We had an input of 4 and an output of 4. So this would be the same as finding a t-chart with your x and y, plugging one number in to get out the output. Okay, so the reason I wanted to bring up these ordered pairs is it directly links to what we're doing here. So again, I'm finding f of negative 3, f of 0, f of 2, and f of 4. I don't have to do any algebra here, so this is done algebraically. This one we're going to do by looking at the graph. So where is the x value negative 3? Well, if we look, here's where x is negative 3. Anywhere along this vertical line, x is always negative 3. And it appears to line up, which is not easy to see in this graph, but I'm going to say that it's about negative 1.75. I'm just estimating here. Negative 1.75. Okay, f of 0, a little bit easier to see, and that is right on the 2. Right on 2. So again, this ordered pair was 0, 2. This ordered pair we estimated to be negative 3, negative 1.75. We go to negative 3, we come down and see where it hits the graph. All right, f of 2. So we come over here, this is where the 2 is, and then boom. So if I get to this point, I know this ordered pair is 2, negative 1. So x is 2, y is negative 1. So f of 2 is negative 1. What is the function at 4? Well, 4 is right about here, and I'm going to go with that negative 1.75 again. Again, we put in 4, we should get out about negative 1.75. Okay, so two different problems. One we did algebraically, and one we did using a graph, so graphically. All right, so we have a little word problem here, nothing big. It says a cell phone company charges $25 monthly fee and 15 cents per minute. Okay, now I know this is a little bit archaic, so let's go with having a monthly fee and then so much per gigabyte of data that you go over. Same idea. So write a function represent the total charge C for m minutes of use. So the total charge is like our y value. We find that to be dependent on the minutes of use. So I'm going to write C of m. C of m is the total cost. So that's my y value. And m is the number of minutes. Not just minutes, but how many minutes. So my total cost depends on how many minutes. So you start with a $25 fee and you add on to that 15 cents. And we're going to do this in dollars. So 25.00, 0.15 every minute. So there's my function. What's the value of the function for an input of 400 and what does this represent? Okay, so C of 400 is equal to 25 plus 0.15 times the input of 400. So I'm going to throw that in here real quick. 25 plus 0.15 times 400. I get that C of 400 is 85. So what does part B represent? The input and the output for 400 minutes the total bill is $85. That's exactly everything you know. In 400 minutes, the total bill is $85. Okay, so this number 8 is talking about parent functions. We're supposed to recognize it with the rule and then sketch a graph. The big thing I also want to focus on is the domain and range and interval notation. So I see that this is a power of 2. And as the year goes on, we're going to get more into these graphs. So that's a power of 2. That means the parent function is a quadratic. Okay, parent function's a quadratic. F of x equals the x squared. Now, the transformation you might not be sure of until you graph it. Okay, so I can tell you that this is going to go left 1 unit. And that is its only transformation. But if we're not familiar with that, we would always build a t-chart. And I'm going to put -2 in, 0, and +2. I might need to fill in some gaps, but that's my start. So -2 plus 1 is -1. I square it, I get out 1. 0 plus 1 is 1. And I square it, and I get out 1. So then I put in 2 plus 1, and I get 3, and I square it, I get 9. And that's a little off my graph. So let's see what's happening here. I put in -2, I got out a 1. I put in 0, I got out a 1. I put in a +2, and that points way up here. So maybe I need to put in, let's put in -1. Okay, I put 0 in and I got 1. I put +2 and I got way off the chart. So let's try -1. -1 plus 1 is 0. Okay, so I get -1, 0. If I put +1 in, 1 plus 1 is 2. I square that, I get 4. So 1, 4. And if I put -3 in, that's also a negative, but it's 2. Squared gets me 4. So -3, 4. There you go. So yes, this is a function. Every x only has one y. It passes the vertical line test. And that's what it looks like. The parent function would have started at 0, 0, and we have shifted left 1. This is in vertex form. Now, the domain, or what the x's can be, we see the graph going up, but as it's going up, it's also going to the left. As it's going up over here, it's also pushing to the right. So the domain is -infinity to +infinity. And the range is the y value. So if we take our pen and we scan, the lowest value we hit here is at y is 0, and it is included, and then it goes to +infinity because this quadratic will keep going up, that parabola shape. Okay, now a lot of us know that this parent function is a line, so we call it linear, and that's simply y equals x, or f of x equals x. So when I go to graph this, I know that my slope is 1 and my y-intercept is -5. Might be something we need to work on this year. So I plot my first point at -5. I go up 1 over 1, up 1 over 1. And that is where I am starting to plot my graph. Now, if I don't remember how to graph a line, anytime I'm not sure how to graph something, all I do is make an XY chart and I grab some numbers like -1, 0, and 1. I just like to start there and then I adjust. So I put -1 in there. -1 minus 5 is -6. So I would go to -1, -6, and lo and behold, there's a point on my graph. 0, -5, and there it is. 1 minus 5 is -4, and so +1, -4. So I could also form my graph. The transformation is that it's going down 5. Down 5 units. All right, the domain is -infinity to infinity. As it goes down here, it's going to the left. As it's going up, it's going to the right. And it's also going down and up forever. So that is also -infinity to +infinity. All right, on the back, we have some refreshers on order of operations and using parentheses properly. There's a lot of negative signs here, so everywhere I replace a variable, I suggest using parentheses. Takes an extra second, but it makes it correct when you put it in a calculator. So the Q is -2 going to the power of 3, and the R is -1, and then we have a -2 and then a -1. So if we follow the order of operations, please excuse my dear Aunt Sally, I would go for parentheses first, and there's nothing in my parentheses to do. So the next thing I would do is I would do my exponent. So -2 to the third would stay a negative, but it'd be -8. I'll have 3 negative signs. I'll leave these other things alone, but you might have worked on them. And here's where you have to be careful. A lot of us want to cancel these negatives or wipe this out. I have to do this power first. So this is what I did first. And now I can go through, leave my -8 alone, and I'm going to multiply a negative times a negative, so +6. Negative times a negative is +2 times 1, a +2. And then I add my number, so I get -2 plus 2, and all of that work, and I got out a 0. All right, next one, 3 times y, which is 2, times x, which is -3, minus 2 times x, -3, times y, which is 2, minus a -3, plus 4 times 2. So lots of parentheses going on here. And when I go to do this, I would leave this alone. You might multiply this chunk, but I'm going to go ahead and leave it alone. Leave my minus sign out there. In my parentheses, I have this chunk and this chunk to do. So this would end up giving me a -12 here, right? -6 times 2. And then when I do this minus a negative, I'll go ahead and change that to be +3. And then plus 4 times 2 is 8. Okay, so this is just addition in there. We'll leave this alone, but again, you might multiply these pieces. And then we are going to put this together. And that would give me what? I was going to go with -12 and 8 being -4. And then plus 3 would be a -1. So it depends on how your brain sees it. That's what I saw to do. All right, next thing, I'm going to come back here. 3 times 2 is 6. 6 times -3 is -18. And then minus a -1 is going to turn to +1. Final answer should be -17. So review of order of operations and watching your negative signs. Okay, last two problems on this review are to simplify each expression. Assume all variables are non-zero because we cannot divide by 0, but know that you cannot have any negative exponents. So we are following our order of operations again, and before I can multiply or move a negative exponent, I do want to distribute that power. So everything inside, including that negative sign, gets a power of 2, and this -3g to the third stays. So a -1 squared would become a +1, and the rule for power to power is that I multiply, so f to the 12th, g to the -6. Really important we know our power properties. And at this point, it's your decision what you do. Maybe you leave the -3g to the third, f to the 12th up here, and because this has a negative exponent, it pulls down and becomes g to the +6. And at this point, we want to go ahead and reduce. So I still have my -3. I would have 3 g's left in the bottom. When we either subtract, we would get a g to the -3rd that moves down, or we cancel out, have 3 left over, with f to the 12th up top. All right. In the next one, again, I want to clean up what's inside before I do my power. So -m is just a negative number. But this negative sign would move up. And notice it's not the 3. Okay. So if I go to rewrite this and put everything to the power of 4, I had a negative up there. I had 7 m's and I shoved 3 more up. That's m to the 10th. Keep my 3. And then there's m to the first, which would cancel with one of these and leave me just an n to the first. Next thing I need to do is everything inside gets a power of 4. So the negative sign to the 4th is going to be positive. A power to power I multiply, so m to the 40th. And then don't forget your 3. One of the things people forget is they forget their numbers. So 3 to the 4th is 81. and that's n to the first, which should be 1 times 4 is 4. So whenever you're done with these problems, no negative exponents. Make sure your m is canceled out and only in one spot. Same thing with your n. Double check for any other reducing of fractions. All right, that is the end of that review.